Hey guys, welcome back. Now, today in this presentation, we are going to focus on a special topic, that is determining probabilities from the joint distribution function. It's not a very complex topic, but a very enticing one actually. So, without wasting any more time, let's begin. First of all, it's my responsibility to introduce myself. I'm Sai Krishna. I'm a student at IARE doing my bachelor's degree in data science. So, what are the objectives of today's presentation? It would be introduction to joint distributions, then going in depth about joint distributions, and a concept known as independence. So, first, do the introduction part. In science and in real life, we are often interested in two or more random variables at the same time. For example, we might measure the height and weight of giraffes, or the IQ and birth weight of children, or the frequency of exercise and the rate of heart disease in adults, or the level of air pollution and rate of respiratory illness in cities, or the number of Facebook friends and the age of Facebook members. Think, what relationship would you expect in each of the five examples above? Why, in such situations, the random variables have a joint distribution that allows us to compute probabilities of events involving both variables and understand the relationship between the variables. This is the simplest when the variables are independent. When they are not, we use covariance and correlation as measures of the nature of dependence between them. Joint distribution is based on joint probability, which can be simply defined as the probability of two events happening together. These two events are usually coined event A and event B and can formally be written as P of A and B. Joint distribution, discrete case. Suppose capital X and capital Y are two discrete random variables and that capital X takes values x1, x2, so on to xn, and capital Y takes values y1, y2, so on to yn. The ordered pair capital X, capital Y takes values in the product x1, y1, x1, y2, and so on. The joint probability mass function of capital X and capital Y is the function P of xi, y of j, giving the probability of the joint outcome capital X to be xi and capital Y to be yg. We organize this in a joint probability table as shown below, like this. Example 1. Roll two dice. Let capital X be the value on the first dice and capital Y be the value on the second dice. Then both capital X and capital Y take values 1 to 6 and a joint probability mass function would be P of I comma j to be equal to 1 by 36 for all I and j between 1 and 6. Here is the joint probability table. Example 2. Roll two dice. Now let capital X be the value on the first dice and let T be the total on both dice. Here is the joint probability table for the specific thing. A joint probability mass function must satisfy two important properties. One is P of xi, y of j must always be between 0 and 1 inclusive. The total probability is 1. We can express this as a double sum, that is summation I equal to 1 to n, ij equal to 1 to m, p of xi, y of j to be equal to 1. Now let's focus on a continuous case. The continuous case is essentially the same as the discrete case. We just replace discrete sets of values by continuous intervals, the joint probability mass function by a joint probability density function, and sum by integrals. If capital X takes values in a comma b and capital Y takes values in c comma d, then the pair capital X comma capital Y take values in the product of a comma b into c comma d. The joint probability density function, that is joint PDF of capital X and capital Y, is a function f of x comma y, giving the probability density at small x comma small y. That is, the probability that capital X comma capital Y is in a small rectangle of width dx and height dy around x comma y is f of x comma y dx into dy. A joint probability density function must satisfy two important properties. That is, f of x comma y must always be greater than or equal to 0. The total probability is 1. We now express this as a double integral. Why? Because we are considering continuous variables as random variables. So the formula would be integral c to d integral a to b f of x comma y dx into dy equal to 1. That is the probability that capital X comma capital Y is in a small rectangle of width dx and the height dy, height dy. Note, as with the probability density function of a single random variable, the joint probability density function f of x comma y can take values greater than 1. It is a probability density, not a probability. In 18.05, we now expect this. Now, joint distributions. You should understand double integrals conceptually and double sums. You should be able to compute double integrals over rectangles. For a non-rectangular region, when f of x comma y equal to c is constant, and you should know that the double integral is the same as the c into the area of the region. Joint distribution, that is events. Random variables are useful for describing events. Recall that an event is a set of outcomes and that random variable assign numbers to outcomes. For example, the event capital X greater than 1 is the set of all outcomes of which X is greater than 1. These concepts readily extend to pairs of random variables and joint outcomes. Example 3. In example 1, describe the events B equal to capital Y minus capital X to be greater than or equal to 2 and find its probability. So the answer would be, we can describe capital B as a set of capital X comma capital Y pairs, and B would include these ordered pairs which satisfy the given condition. We can also describe it visually like this, where the shaded orange region is nothing but the set B. Event B consists of the outcomes in the shaded squares. The probability of capital B is the sum of probabilities in the orange shaded squares. So, probability of B is equal to 10 by 36. Now, let's take another example. That would be, suppose capital X and capital Y both take values in 0, 1 with uniform density. F of x, y is equal to 1. Visualize the event capital X is greater than capital Y and find its probability. So the answer would be, jointly capital X and capital Y take values in unit square. The event capital X to be greater than capital Y corresponds to the shaded lower right triangle below. Since the density is constant, the probability is just a fraction of the total area taken up by the event. In this case, it is clearly 0.5. So joint distribution, joint commutative distribution function. Suppose capital X and capital Y are jointly distributed random variables. We will use the notation capital X to be greater than or equal to less than or equal to X, capital Y to be less than or equal to Y to mean the event capital X is less than or equal to X and capital Y less than or equal to Y. The joint cumulative distribution function, joint CDF, is defined as capital F x comma y to be equal to P, which is where x is less than or equal to x, and y capital Y is less than or equal to y. In the context of continuous case, if capital X and Y are continuous random variables with joint density f of x comma y over the range a comma b into c comma d, then the joint CDF is given by double integral c to y integral a to x f of u comma v du into dv. To recover the joint PDF, we differentiate the joint CDF because there are two variables we need to use partial derivatives. F of x comma y to be equal to dou square f by dou x dou y x comma y. Discrete case. If capital X and capital Y are discrete random variables with joint probability mass function p of xi comma y of j, then the joint CDF is given by the summation. That is, so if capital F x comma y is equal to summation xi is always less than or equal to x y, and do cap yj is always less than or equal to y, p of xi comma yj. Let's talk about properties of joint distribution. The joint CDF capital F of x comma y of capital X and capital Y must satisfy several properties. F of x comma y is non-decreasing. That is, if x or y increases, then capital F x comma y must stay constant or increase. Capital F x comma y is equal to 0 at the lower right of the joint range. If the lower right is minus infinity to minus infinity, then this means so limit x comma y tends to minus infinity comma minus infinity, f of x comma y to be equal to 0. Capital F x comma y equal to 1 at the upper right of the joint range. If the upper right is infinity comma infinity, then this means limit x comma y which tends to infinity comma infinity, capital A y f of x comma y to be equal to 1. Example 6. Find a joint CDF for the random variables in example 5. Answer. The event capital X is always less than or equal to X and capital Y is always less than or equal to Y is a rectangle in the unit square. To find the CDF f of x comma y, we compute a double integral f of x comma y to be equal to 0 comma y to 0 comma x a u v du dv is equal to x square and y square. And example 7 is pretty much the same thing, but let's see that. In example 1, compute f for 3.5 comma 4. The answer would be we redraw the joint probability table. Notice how similar the picture is to the one in the previous example. Capital F of 3.5 comma 4 is the probability of the event x is less than or equal to 3.5 and y is less than or equal to 4. We can visualize these events as a shaded rectangle in the table, and this would be this. The event x less than equal to 3.5 and y less than or equal to 4, adding up the probability in the one shaded squares, we get f of 3.5 comma 4 to be equal to 12 by 36 equal to 1 by 3. Note, one unfortunate difference between the continuous and discrete visualizations is that for continuous variables, the value increases as we go up in the vertical direction, while the opposite is true for the discrete case. We have experimented with changing discrete table to match the continuous graph, but it caused too much confusion, which we'll just have to live with the difference. Now, this is an important topic, that is independence. We are now ready to give careful mathematical definition of independence. Of course, it will simply capture the notation of independence we have been using up to now. But it is nice to finally have a solid definition that can support complicated probabilistic and statistical investigations. Recall that the events A and B are independent. So if a P of A intersection B is equal to PA into P, we would do that. Random variable capital X and capital Y define events like X is less than or equal to 2 and Y is greater than 5. So capital X and capital Y are independent if any event defined by capital X is independent of any event defined by Y. The formal definition guarantees this is the following. And the definition is jointly distributed random variables capital X and capital Y are independent if the joint CDF is the product of the marginal CDFs capital F x comma y equal to capital F x into x and blah. For discrete variables, this is equivalent to the joint probability mass function being the product of the marginal PMFs. For continuous variables, this is equivalent to the joint PDF being the product of the marginal PDF. Once you have the joint distribution, checking for independence is usually straightforward, although it can be tedious. And this is another example which showcases the same. And this is another example which showcases the same. Well, guys, thank you for tuning in. I hope you have learned much about the probabilities in the context of joint distribution function. Let's see you in another video. Till then, have a good one. Bye.